You may experimentally measure the relationship between stress and strain. Various parameters are measured by using the metal testing machine introduced before. The parameters are shown in the stress-strain diagram. First, we focus on the point of P in the diagram. From the origin to P, the slope of the stress against strain stands out. In other words, P is the limit of the range in which stress and strain are proportional. The point of P, the maximum value of the range, in which the relationship between stress and strain is proportional, is called proportional limit. The point, elastic limit, which is neighboring the proportional limit, may be a bit confusing. The proportional limit should have been easy to understand as the limit of a proportional relationship between stress and strain. The elastic limit is generally a little bit above the proportional limit. You should be noted that the elastic limit is just a little bit above the proportional limit in reality. Some textbooks may say that the elastic limit is almost equivalent to the proportional limit, but for the clarity, the point is shown at a higher location in this diagram. So, what happens if the load exceeds the elastic limit? Permanent deformation occurs after exceeding the elastic limit. The plastic deformation, which has been already explained several times, occurs. For example, when plastic deformation occurs, a bent wire remains bent. A depressed thin plate remains depressed. As these phenomena, even after the removal of loading, strain remains, and the material does not return to the original position. Here, you should be noted that the value of the proportional limit and the elastic limit are very close, but they have slightly different meanings. So far has been the argument about how to distinguish proportional limit and elastic limit. Next is about tensile strength. When a material is stretched or pulled, the stress, which is on the vertical axis in the stress-strain diagram, reaches at its highest. The stress here is called tensile strength. The tensile strength is defined as the limit of stress that a material withstands. The value of tensile strength is essential when designing a structure. For example, we have a round bar here. With its diameter, we can determine the cross-section area. Then, we can derive the maximum load that this material withstands based on the product of tensile strength and cross-sectional area. The value of tensile strength is used to evaluate whether a structure holds or withstands loads required in its operating environments. Here, you may realize that the tensile strength is almost a marginal value. For example, suppose you get the tensile strength as 400 megapascal and find that a structure can withstand loads of up to 5 tons. On the basis of the value, up to 5 tons, you may select materials and design the structure. In this case, however, you should note that no extra loading is allowed on the structure. In reality, tensile strength is used to design structures and mechanical parts with the margin of loading. The concept is safety factor, which will be explained in detail later. Just for now, you should learn that a structure design should have margin of loading for its safety. Now, you should be familiar with proportional limit, elastic limit, and tensile strength with respect to the explanation before. Next is about yield stress. This is a typical stress-strain diagram of mild steel and its properties. Mild steel is a type of carbon steel, a steel that includes carbon. It may be a material commonly known as iron. Among carbon steels, mild steel is considered to be soft, while hard steel is considered to be hard. Mild and hard steels are generally distinguished by their carbon content. Mild steel normally has a carbon content of less than 0.3%. Steels of a carbon content lower than 0.3% show a very specific characteristic in stress-strain relationship. When it reaches yield stress and starts plastic deformation, as you see in the stress-strain diagram, the load or stress rapidly drops a little. On the curve of the relationship between stress and strain, the upper point, at which the curve shows linear rises and falls, is commonly called upper yield point. This lower point, the fluctuating region, in which materials plastically deforms instably, is called lower yield point. Together, they are called yield point.